Thank you. I'm very happy to introduce to you today Negar Kiyavash, who is the chair of business analytics at École Polytechnique Fédérale de Lausanne at the College of Management of Technology. Before coming to EPFL, she was a faculty member at University of Illinois, Urbana-Champaign, and also at Georgia Tech. Her interests are broadly in the area of statistical learning and applied probability with special focus on network inference and causality. We're very happy to have Negar here, and we're looking forward to your talk. Thank you for being here. Go ahead.
Thank you, Mariana. So this is a pleasure, of course, to give this talk to you guys. So today I'm not talking about causality, incidentally, but it's a type of network also inference, as Mariana mentioned, that is the focus of my research, especially in recent years. So specifically, I'm going to talk about various alignment problems. So this is actually joint work with my former and current students. So Daniel Kalina, who is a faculty member at Penn State, he was essential in carrying out this research, and Osman, who is my student close to finishing at Georgia Tech. So of course, we all know that these days we are subject to data collections from many sources, and whatever we do, pretty much, we are giving away data. So these diverse data sources allow data junction that could possibly increase the benefit to various either us as the users of these systems, also as providers. But also sometimes data junction is not as obviously possible as we think, and the reason for this could be that data could be anonymized for security reasons, and this could create some complications in terms of data junctions. However, often there is some correlation among data that allows us possibly to do non-trivial alignment and as a result inference and data junctions. On the flip side, this clearly can also pose a risk to privacy. So it's crucial for us to understand conditions that allow us to preserve still privacy, do data junction, or breach the privacy. So to just give a higher level idea of what kind of objects I'm talking about this talk. So I'm talking about this so-called notion of alignment. When we talk about alignment, we have data that comes from multiple sources. Everywhere in this talk, I'm going to limit myself to 2 sources. So we could have, for instance, 2 data structures that is depicted in this picture. And these data structures have users, like you could have the blue user or the green user. And this data could be available across either both of the sources or in some cases in only one of these databases. As an example, you can see that the green and the blue appear across both databases, but the other users only appear in one database. So then it, as I mentioned, because of privacy concerns, often this correspondence is obfuscated or unknown. And the goal is that can be used actually this correlation among the sources and still understand that which one is which user, right? So the goal is to identify the correspondence between users in various data structures. So this data could be, again, when we talk about sources, could be data associated to single users. So in this case, I talk about like database alignment. Like, let's say these are medical records of various individuals across various institutions. Or it could be type of data that actually has some interaction between the users and the objects, right? So this would be so-called bipartite alignment, when you might have a situation like, say, users are rating some objects, say movies. Or you might have interaction between the users, so you can think about connections over a social network. So then this problem is called graph alignment. And of course, you can have combinations of these type of problems. So for the first part of the talk, I would focus on database alignment. And then I hope that this database alignment would allow us to understand what is the gist of ideas in this area. And then I would talk a little bit about also what is known in terms of the graph alignment. So to give an illustrative example, I want to give one which actually comes from the middle setting, which is this so-called bipartite alignment or movie ratings. So Netflix Prize was a data set that was comprised of user IDs and movies, and then the ratings of those movies. So on the left, the dots are indicative of the various users, and then on the right-hand side, the squares are movies, and each user might have rated a subset of these movies and given them various ratings. So there is this other database, IMDb, that if you're into movies, most likely you have seen it. And then in this IMDb, actually, you have this situation that you can have usernames and then have also the name of various movies and ratings of those movies. So it's common for IMDb users to actually register with their full names, and these users may avoid publicly rating certain movies that even though they're interested in, they avoid that. And the reason is that, you know, when you're interested in movies, it actually gives away some information about you, right? For instance, movies you like might tell something about your political views, your religious beliefs, or sexual orientation. So it was shown that actually many Netflix user IDs, it was possible to match these obfuscated Netflix IDs to the public IMDb profiles, which actually allowed people to get de-anonymized, right? And what is the problem here? Then, you know, you can understand what other things were they watching or rating in possibly Netflix. So Netflix actually ended up facing a class action lawsuit, and even though they had some competition, which is very famous in this area, I think at least those of us that are more senior, like around my age, we all remember this was a big deal, this Netflix competition and so-called matrix completion problem. They had to indeed cancel the sequel to this, and the reason was because of this de-anonymization that was happening because of this bipartite alignment. So I hope I have now at least told you that this is not just some nice problem. Actually, it has a lot of applications that could have serious ramification. So let me try to explain what is this database alignment, at least in some abstraction, and what are the things we know about this problem. So when we talk about databases, right, we're often talking about this unordered set of features that are each associated with a user. So this is what I'm showing here with these black lines. And you could have various users across various databases. So as I was saying in this talk, I would stick to two databases. So you have database A and database B. And of course, there's correspondence between these users. And what we're going to assume is this. So we're going to assume that in each of these databases, the features are IID and identically distributed. But for the same user, across the databases, there's a joint distribution of these features. Again, if you're looking at user pairs across the databases, these guys are also independent and identically distributed. So basically what it means is that features of a user are always independent from all the other features, right? But they're of course correlated for the same user across the databases. So I'm going to use also this notation, cal-u and cal-v, which is the set of user identifiers. And you can think about it could be someone's name, or it could be your social security or any other identifier, right? And m is a mapping between these identifiers. So also, some other important notation is this. When I talk about W of M, these are pairs that are mapped by this matching. So whenever you have this map, that could either be a perfect matching or be like a partial matching. That's why I use the word mapping. So this mapping M can have pairs in there, or it could also, when, you know, so you can consider only the restriction of this map to the set of users in one database. Then we use this notation UM and basically VM, which one of them is mapped users from database A, the other one is the mapped users from database B. So we have, as I mentioned, also these arbitrary features for each of the databases. I'm going to call them by X and Y, corresponding to these two databases. And of course, I'm going to have these marginal PDFs, or it could be if you're, you know, in some situations, we're actually talking about the discrete alphabet, so it would be PMF. So I'm always using the same notation, although usually F is used for continuous variables just to not change notation during the talk. And then we have this FXM condition on M, which is the joint PDF, or again, the joint PMF of the features for a user given a certain matching. we assume all throughout the talk that these distributions are known. So then if I have this, I can easily write a log likelihood for these databases given a mapping M. So what is this log likelihood? Just a quick question. When I highlight, can you guys see the highlights on the? Okay, perfect.
Yes.
Thank you. So basically, if you want to write the likelihood, this is how we can write it. So condition on a mapping M for any pair of users that are part of this matching, I can write the log for the joint. And then for those of them that do not get matched via this mapping, then I would just have their marginals, which is the last two terms here. Of course, I can also just rewrite this, and there is nothing clever here. I'm just basically adding all the users to these sums and then removing the extra terms that I've added by having them in the denominator. And in a second, you will see why I'm doing this transformation. Doing this transformation actually allow us to get rid of the last two terms whenever we are doing calculations, because now there is no dependence anymore on the matching, right? So I've basically put everything that depends on the matching in the first term. So obviously, if we have now this notion of likelihood that we have, we can talk about, if your goal is to learn this matching, right, learning the pairs, when you have a likelihood function, the basic idea is that you might want to choose the one that maximizes such likelihood. And in this case, what I can do is that I can make this a matrix of information, which let's look at what it has. So of course, these values are these logs that I have here. And then what they end up having is that, my apology, I should have turned off my mail notifications, but bear with me, please. I hope I don't get a lot of emails. So this matrix has the dimension, which is U cross V. This was the size of the users in the two databases. And I can talk about this basically information density matrix, which is just each of these basically values that are appearing in this summation, right? And then when I talk about a matching is indeed has this property that I have a matrix that encodes my matching, and I would have either an entry 0 or 1. I would have a 1 whenever these pairs U and V are part of this basically mapping M. Otherwise, there is a 0 there, right? So this is just this definition that I have. So very clearly, one other notation that you can use to write the maximum likelihood would be that, you know, you write it as an inner product between these two matrices. It's nothing clever, just like, you know, to rewrite this formulation. So clearly this G is a function of random databases, right? And it's something that we can compute as long as I have the distributions, which is what I assumed I have, right? So in general, this M, the map, is a partial permutation matrix. And if we know the cardinality of M, then maximizing this likelihood function is actually equivalent to a linear assignment problem. And this is something that we know very efficient algorithms for it, like namely, I mean, of course, efficient is a matter of what field you come from, but these are polynomial time algorithms, right? So we can actually use the Hungarian algorithm to solve this, this linear assignment problem. So therefore, in general, we can do the ML in polynomial time. However, this MLE has to optimize over all mappings. So indeed, even though this is a polynomial time algorithm, in general, this can actually be quite exhaustive. So in practice, especially for a lot of big problems, we might be interested in actually simpler and faster approaches, right? So what are some options there? So one thing we might do is this so-called, of course, it's a suboptimal thing to do, is this notion of max row alignment, right? So what does this algorithm do? So given a user in one of the databases, let's say in database A, you only find features in, you know, database B and ignore all the other features in A. So this is really just doing this max row alignment, right? So it ignores everything else which is in A, and then picks actually a feature in B that is maximizing the likelihood with this basically user. This is basically equivalent to picking the max entry in a row of G, and it's not surprising that this equivalence exists. You could even be less ambitious and just do the basically most simple idea, which is thresholding, and you decide if a given feature pair is correlated and if this correlation is large enough for you, right? So you basically do some likelihood ratio test with some predefined threshold, and this is, you accept that there is a pairing as long as this correlation is high enough, and this corresponds to entry of G being above a certain threshold. That's what it means, just that correlation is high enough for you. So what does in this setting, what can we say? So what is known in the area are as such. So if the features in A and B take values from some finite alphabet, then there is a critical notion of actually how much correlation is between these databases, and is captured by this notation I circlet, which in a second I'm going to tell you what it is. And then I'm going to give you the results for a very in general, like, you can have different sizes for these databases, but just to make everything easier, I'm going to assume that here we have the size of everything is, both databases are the same, and you have like a exact, like, alignment, so you don't have a partial matching. And then let's say the size is n and n is large, right? So what is the MLE telling us? So it basically, we have this achievability result, which tells us that the maximum likelihood estimator can find the correct probability, can find the correct mapping with probability going to 1, as long as this relevant basically measure of information exceeds this 2 log n, right? Similarly, we have a converse. So if the critical information value, this I, is less than this 2 log n, then any algorithm would actually fail with probability going to 1 again here. So what is nice, if you notice, is that this is a tight result, right? So basically your converse and the converse and the achievability are matching. And this basically tells you, as long as you have enough correlation between the databases, then you can match everyone reliably. And if you don't have this much correlation, then you cannot match everyone reliably. So what is this I that I have here? So in this special case, right, so that the size of your matching and the two databases are the same, the smallest number of the errors the estimator can make is 2, right? Because you have to match everyone. So if you're making a mistake on one user, it means the other user is also wrongly paired. You're forced to make at least 2 errors, right? So in this setting, then if I have 2 mappings, let's call them M and M prime, that only differ at 2 pairs of users. So it's the minimal errors that you can make. So for instance, let's say M is the true mapping and is correctly pairing user 1 across both databases and the user 2 across both databases, versus M prime, which actually is switching these 2 users. So it makes the smallest possible error, these maps. Then this I is the Bhattacharya distance between the distribution of the databases, assuming this was the true matching, either M or M prime. So basically, this is just to like recapture, these are the results that we had in terms of this critical value. Sometimes we might have actually non-finite databases, and one interesting case is if, for instance, you have the Gaussian database, where it means the features in each of these databases are vectors, and then these guys are multivariate Gaussian, right? So the distribution that we are working in. So here, this critical actually information is something that most of us are familiar with. It just pops out to be the mutual information between these correlated features. And again, as you know, mutual information is indeed the Bhattacharya distance here too, when you're looking at this adjacent mapping across these data sets. So what are the results here? We have very similar achievability and converse to what we had before, except that in case of Gaussian databases, this critical value is not that I circlet before, but it's this other basically relevant Bhattacharya distance, which is the mutual information. But as you see, again, these are matching converse and achievability bounds. So these results actually consider success. They're very ambitious, right? You say you only succeed if you have exact matching. But as I was motivating the problem, let's say when you want to de-anonymize users across the databases. It's very ambitious to think that, you know, you only breach privacy if you can match everyone. Even if you match enough people, that could also be considered a breach, right? So namely, you know, what if your estimate is not exact, but the ratio of the errors are vanishingly small? This is still a pretty disastrous case in terms of what you can actually match if you're trying to breach privacy. Or if you're trying to do data junction, actually it's good, right? So even though users were obfuscated, you could still connect them across the databases. So the results here, which is on the lower part of the slide, is very similar, except that if you note there, I had this 2 in front of log n, so now this 2 vanishes. So the threshold changes. What does this mean? It means I don't need as high of a correlation that I needed for the exact matching. So as long as, you know, I'm making vanishing number of the errors, right? So it's then the threshold would be this log n. And again, we have here matching, converse, and achievability. So this is a result that is known here. So I would like to take a few minutes and show this graphically, because I think sometimes it becomes easier to look at this than, you know, having all these asymptotics that, you know, are hidden in the Lando notation. So let's see this graphically. So before I show the graphs, I want to explain what is my axis. So here I have this axis that, you know, I have an x-axis and I have a y-axis. So let's make sure we understand what these are. So for instance, I'm going to show this only for the Gaussian case, in which case your x-axis, I'm going to use this notion of the basically mutual information. And my x-axis is going to be normalized mutual information. So this is just IXY divided by log n. And my y-axis is actually my so-called error exponent, right? So what do I mean by that? So it's the expected number of my errors are growing as n to the y, and this y can be thought about as your error exponent. So in this setting, so I'm just showing this, as you see, the x-axis is just this normalized mutual information. And then I'm also on the y-axis showing basically the normalized, and so it's basically the exponent, right? So it's just log of this quantity divided by log n. So what are we showing here? So if you look at this y-axis, there is a line here that I have highlighted in blue. So this is where you make constant number of errors. Above this line, which is basically this purple part, it's basically that, you know, you have the almost perfect alignment. And if you look at the blue line here, where your exponent is getting larger, right? So you make constant fraction of errors. On the bottom of this line, blue line, we have this small o of 1. So basically, you have perfect alignment. Number of your errors are basically going to 0. So this is the notion of what? Yes.
We have a question on the chat. The question is the joint distribution known, or does it have to be estimated from the matched pairs?
This is an excellent question. So we assume the joint distribution is known. We are learning the matching. So our goal is to do the alignment, right? So we do not assume that you don't have the distribution. Of course, as you can imagine, you can do this like in reality, you might want to do both, right? So you might do some sort of expectation maximization type of idea, right? So you assume a mapping, then, you know, you estimate a joint, and then try to then, you know, from that learn the mapping and so on. But for the theoretical results, we assume that, you know, the joints are known. Thank you so much for the question. So let's remember this then. So the important thing is this. So when you are below the blue line, we have perfect alignment. This is where you have, you know, vanishing errors. And then, you know, when, you know, basically you make no errors. And when you go above that, you either have constant number of errors, and then, you know, you can have also really a disastrous case where this is this constant fraction of errors, right? So let's remember that. So the results I was showing to you, let's see what is the meaning of this converse, right? So I was telling you if my correlation is less than this 2 log n, then this is a hopeless setting for me. And this in the axis that I have introduced here ends up being this highlighted area in red. So it means that you basically have no hope of getting vanishing errors, right? So this is something you cannot achieve. You have so, you know, you cannot have the exact alignment in this setting. On the other hand, the converse, which was the weaker, and I had this one that, you know, you basically get, so you can go basically higher up in this region. And this was in the case when I was telling you that, you know, we don't have the exact alignment, but we have the almost exact alignment. But it, even in this setting, if your correlation is too low and the low here is different, it's log n instead of that 2 log n, you would get this basically red region, which is not something that you can actually achieve. So now let's look at what are our achievability results. So if we were looking at MLE, right? So the MLE achievability region, if we just do some calculation, ends up giving us this green region. And the low correlation setting, right? So this was the one that we were okay if we did not get an exact alignment, right? But nearly exact alignment. This gives you this little extra kind of, you know, circulant region that you're adding here. It makes this possible to achieve. So similarly, if you were doing something simpler, right? So you only care about the max row, then this max row would give you this other region, which is like, you know, defined by this line here, the blue line. And if you were doing the thresholding, then, you know, this basically region is now going to be defined by this other line, which is, I guess, cyan or whatever you call this color. So this would be capturing this threshold region, right? So this is the meaning of the results. So based on what you're using, you capture various types of, like, you know, events. So, and all of these are actually algorithms, have this property that above the converse, right, they make ON of errors, right above the converse. And this was something that was actually discovered in a work of my friend Elsa and her students. So this is something that, you know, is also consistent with other work in the literature. So this nice thing about this database alignment is that actually it allows us to get insight on information theoretic quantities that characterize limits on alignment problem in general. And then why is that the case? I just hope that it's like, you know, at least if it becomes clear later when I describe some of these graph matching problems and so on, that you can think about in certain limits, they start behaving like the database, right? So it also has importance in other setting, understanding the case of the databases. So I do not like going to these plenary talks that are just laundry list of results. So I thought at least for the middle part of the talk, I want to tell you a little bit how we did this, right? So it won't be like a boring in terms of like not knowing what are the derivations. So I hope it's okay with you. So I want to spend like around 15 minutes telling you, like, at least in some cases, how are these results, you know, derived. So let's remember that I was doing this matching, that I was using a matrix representation that was the M, and I had a 1 whenever we had a alignment, right? So this, let's say for now that, you know, you were in this setting that you have 5 users, and then, you know, like without loss of generality, the same indices correspond to the correct matching, right? So this would be our correct matching. And you could possibly make a mistake and not consider the correct matching. And if one such a mistake is just depicted on this slide, which is this M prime, which does a correct job, like as you see, this M prime can actually match the 2 users, U1 and V1, but it switches U2 and U3 with V2 and V3. And then it actually makes this other problem that, you know, here is the reason is because the size, if I had this setting that size of my second database was larger, you could even make mistakes that are not anymore cycles, right? You could get these so-called paths, right? And then it actually ends up putting the ones in the wrong spot in this matrix. So specifically, if I was looking at the difference of these 2 matrices, we always end up getting something that looks like this, right? So you would either have -1s or +1s. And they appear in these blocks, which correspond here, right? So when you don't have a mistake, you just have a 0. Whenever you have a mistake, you can have one of these settings, right? So the blue one is this so-called cycles, and then you can also have the orange one, which is the path in general. So if I'm considering some matching M prime, And then, you know, as I said, it induces a bunch of these blocks, like, you know, let's just for now think that there were 2 blocks that you had actually induced here. Then there you can have 2 other mappings, M'1 and M'2, that you can actually just consider these 2, and each of them is just this partition of having the first chunk of the mistake pertaining to H1 and the other one, the chunk of mistake that is coming from the second one. So then if I was looking at this inner product, and remember that this GM was what I was maximizing, right? It was my maximum likelihood idea was that I was working with this object. I can just decompose it into 2 parts. So for me, in a sense, it suffices to study each of these parts, right? So if I'm making a mistake, the reason I'm making a mistake is either because, you know, so I end up like taking the erroneous match. So it means that if I was taking M prime, this inner product is larger in M prime than the true matching, right? And this happens either because it was happening at the first one or it was happening in the second one, right? So you can basically decompose the problems and just look at basically these single components or the blocks, right? We don't need to worry about other settings. So let's say now for like, you know, in this case, M is the true match and then M prime is some false mapping. So again, recall that what I discussed is that a user is mapped at most once by M and then at most once by M prime, right? So you always have this fact that each node only appears basically at most once at a blue and at most once at a red match, right? So this is just a property. So all my components, as I explained, all these errors are either cycles or their path. Specifically, just to make things easier, even though we had to analyze all of these, when the size of the databases are the same, I don't need to worry about 2, 3, and 4. I only need to worry about these so-called cycles, right? Because the size of the databases is the same. You just need to worry about cycles, right? So I'm going to stick to that to give you a gist of how this proof works. So let's say M prime was our false mapping, and the cycle that it ended up inducing was something of length 4. If that's the case, I can just use the Chernoff bound, and the Chernoff bound exactly tells you this like probability of actually making such a mistake. And you can see that it would be XP of this minus I, where recall that I was the Bhattacharya distance of relevance, right? In case of finite alphabet. And it would be XP of minus mutual information in case of you were using the Gaussian databases, right? So, and then what we can do is that, you know, note that this does not have to be a cycle in general. It doesn't have to be a cycle of length 4. It could be in general some cycle of like 2 delta. And if that's the case, instead of the exact, you will still get an upper bound on these error probabilities, again, using a Chernoff bound. And now, as you see, there's this delta over 2 terms in here, which when, you know, this delta was 2, hence you had a cycle of length 4, it was just canceling. We weren't seeing it in the previous expressions. So just to, again, like make life easier, I'm just going to stick to I because they look the same, right? So of course, in different problems, these are different objects, but let's call this correlation measure just I generically. So if I'm considering these basically false mapping that induce cycles of length 2 delta, how many of these we would have? We would have this like basically value of delta choose n, delta minus 1 factorial, which is upper bounded by this quantity n to the delta over delta. Hence, what I can do is now like just calculate the expected number of cycles that are contained in this basically erroneous mapping. And this is not difficult. We had done this calculation in the slide before. And now I'm just using this upper bound on the number of such things. So this is the expectation, right? This was the probability. This is the number. It gives you the expectation. And then this cycle of length 2 delta results in giving us delta errors. Remember, right? So if I was making a mistake between 2 users, it was a cycle of length 4, right? So it always, every 2 delta cycle is giving me errors of size delta. Hence, I can just multiply this by delta. So this delta goes away. And I need to sum up, like doing some sort of like union bounding over this over all possible cycles, right? Hence, I get this expression, which is just, of course, and this could be in general loose, right? Because this is not, this can double count and actually triple count and multiple times count the user. But recall that the user is only part of one matching, but it still is okay for the analysis, even though this could be loose in general, right? So I have this union bound, and something nice happens if my correlation is large enough. So by large, I mean this 2 log n, then what we see for this like geometric series, we see that, you know, this it's upper bounded by this value, a squared over 1 minus a, and this is basically the value of my a. And specifically, I can show that if I just go a little bit above this 2 log n, then this is going to converge to O of 1. So then we're good, right? So basically, this is a setting that I make sure that I make no errors. So this was the exact alignment. So this is the analysis of the approach that we had to do. So the analysis of the approach gets much more difficult if we want to look at the low correlation regime and you know, not exact matching. And we can actually not anymore use this simple union bounding technique. It doesn't, you know, it can't handle all the redundancies, and it becomes much more complex, but at least we get an idea of how these things are done. So this is the case of this so-called database alignment. And another set of problems that are of interest to folks, and this actually is a very old problem going all the way back to Erdos, is this notion of graph alignment. And this is what I briefly told at the beginning, that, you know, you can have actually users are also interacting. And let's look at this, and I hope you would see in a second that why this is a much harder problem. So in this setting, I have 2 networks, right? So my data consists of actually edge information. So you can think about it as two social networks. Let's say on one of them, users' IDs are known, like something like LinkedIn, while another one could be another database where people have hidden their IDs, but your connections might still be there, right? So if you're connected to someone on LinkedIn, you might still be connected in this other social network with them too. So these edges are basically containing the information in terms of which user is connected to whom. And the graphs don't have to be exactly the same, but there is a correlation in terms of like when edges exist between these. So the correlated graph model can have various settings. So one of them is this, right? So you might assume that your edges are IID random variables, and then they're likely to, you know, that the edges are more likely to appear in both graphs than appear in one but not the other one. So this basically means the graphs are correlated, right? That's the notion of correlation that, you know, we are discussing here. So in a classical setting, these edges are often Bernoulli random variables, and, you know, they basically either exist or don't exist, right? Other settings of interest are so-called arbitrary discrete alphabet that allows modeling of different type of connections in a network, right? So it's not that you just have an edge that exists or not exists. You might have a certain type of edge, right? So obviously generalizes the Bernoulli case. You can also have settings when you have continuous vector spaces. So one special case which people have worked on intensively, at least in the recent years, is when you actually have graphs with Gaussian weights. So graph alignment has these ingredients in terms of how things are modeled. Again, I have this fx and fy, which are my marginals of the edges in the 2 graphs, right? So this is for edges, not anymore these features pertaining to vertices. So there's always at least a pair of users in every graph, right? Then I have this fxy, which is the joint of correlated edge pairs, right? So I hope that this is clear now, that, you know, the objects that I care now are the edges, not just the vertices. So this edge correlation between the 2 graphs, and still I want to use this correlation to find the vertex correspondence. So I have this mapping WM that actually pairs the vertices, and you can of course lift this, because every pairing of the vertices also you can just lift it and see what is the pairing of the edges, right? So I'm going to use this basically to choose S to denote all subsets of S that are of size 2. Then in that case, I can have now notion of the likelihood for the graphs. That let's look at this object, make sure we understand it. So there in the databases, I was just looking at the pair of vertices that, you know, belong to this mapping. Now I'm going to consider these basically subsets of size 2, because I'm lifting this to edges. And then each time you match an edge, of course, it's a pairing between basically these vertices, right? So for instance, you would have a vertex in the first database, right? So it has been mapped one side of the edge with one side in the second graph, and vice versa, right? So you have these basically mapping for these guys. And then I can again talk about the likelihood, which this likelihood is between these notion of my databases, which are truly now these graphs, and then this A would be always a pair here, and B also is a pair because I'm doing this matching between the edges, right? Not vertices anymore. And then we have these objects that we are considering. Now I can again define this notion of my so-called information density matrix. The difference is now it's like a larger, of course, dimension that I have to consider. All, you know, you always have these type of objects, right? So you're always matching ends of these edges. So each of them is a pair UV, right? So you look at this basically space for your matrix G, and here my M is going to be a vector, right? So it's a vector, which is, as you can see, it's basically of length U cross V, and it has ones whenever you actually matching a certain pair of edges. So that is what this would look like. Hence, I can define my maximum likelihood estimation now as this object, which is going to look at this quadratic assignment problem, right? And then these constraint here are just making sure that, you know, you're not violating the fact that these things are indeed matchings, right? So you have to do the right number of pairings across each of the databases. So recall the database alignment problem. It was an easier problem there, right? So I was basically doing this maximization, which you can see that, you know, it ends up being this trace function. Hence, you are doing a linear assignment, while in the other class that we are considering, you end up looking at this quadratic assignment problem. As I was telling you earlier, of course, the linear assignment, you can, you know, you can use the Hungarian algorithm, and this is cubic in n, while in general, the graph alignment is a quadratic problem, and the quadratic assignment is NP hard. So given that this is NP hard, then it's not surprising that this is, you know, algorithmically, at least this is a very interesting problem. But in fact, even information theoretically, when you don't care about the complexity, still it's a very difficult problem to know what amount of correlation makes things good or not good. So I'm gonna, in the remaining time of my that I have for my talk, just tell you what are the results known here. And I'm gonna describe them in some settings that are best studied, namely when you have correlated Erdős-Rajnyi graphs. So what is this? So I have a pair of graphs on the same vertex set, and they have different edges, and I'm going to assume that I have n vertices in each of these graphs, and then I have an average degree of np. So remember, n is number of my vertices, p is telling us what is the density of these graphs, right? So it's capturing the average degree. I'm interested in this object, which is the intersection of the graphs, which is basically telling you how correlated these objects are. And this is also an Erdős-Rajnyi, and I'm going to assume that, you know, this is given by this NPS. So S, in a sense, is the parameter that captures. So remember that P was capturing the density. S is capturing, in a sense, how correlated these graphs are, right? So, of course, I can also look at the difference of the graphs, and this is, again, Erdős-Rajnyi, and then my average degree here would be NP1 minus S. So, one way to think about it is that, you know, so these graphs are as if, you know, now, you know, each of them are each edge is generated as such. So the fact that we have these properties, an edge existing in the intersection happens with probability PS, being in one but not in the other is P1 minus S, and an edge, you know, basically not being in any of these is this 1 minus P2 minus S, right? So these are the quantities of interest, right? It captures basically all these probabilities of interest. So what is known here? I'm gonna just give you the results here, and first I'm gonna describe to you what kind of axis I'm checking here. So I'm gonna have this y-axis, which is the notion of strength of my signal, right? So let's make sure it's clear here why I'm calling this object strength of my signal, because remember, the more correlated two things are, so they share more edges in the intersection graph, they're of course more correlated in some sense, right? So it's not surprising that my measure of correlatedness or strength of my signal is this value PS, and I'm just normalizing this by log n, right? So what does this then look like? I have these this blue line, which is it happens at when the y-axis is -1, and this is where you have constant average degree in the intersection graph. If you are below this line, then the average degree in the intersection graph is O of 1. If you are above this line, then the average degree is theta n of y in the intersection graph, right? So it's basically telling you how strong your signal is. So how much intersection you have, or how correlated these graphs are. I also care about this x-axis, which is the amount of noise, right? So what is this noise? It's these mismatches that you have between these pairs. And remember, this P1 minus S was capturing that, right? So I have these interesting regions. So I could be either in a very noisy region. What I mean by very noisy is that, you know, you have constant number of edge differences for each vertex. I have this so-called noisy one, which is intermediate. And then again, I have constant number of edge differences, but it's not for a vertex, it's between the graphs, right? So it's a much better scheme. And then you have the noise-free, which is the classical setting, right? So it's basically to this side. So we are also interested in, actually it's not, I mean, we have results also for the case we have negative correlations, but most research in the field has looked at the case when you have positively correlated graphs. And by positively correlated, I mean that probability is that the edge is in neither times probability that is in both is always larger than this probability that the edge exists in one but not the other one. This is the notion of the graphs being positively correlated, right? And if we were to just do the math here in terms of our axis, we would see that, you know, in the basically sparse regime, which is of interest, right, for most of the results, again, look at the difficult setting where you have a sparse graph, this correspond to this y over x, my axis is being larger than 2. And this is exactly the line here. So this is the line here shown, that we do not consider the gray zone, which is the negative correlation. We're going to just consider what's going on in this positive correlation zone. And these are the results. So the most classical is of Edward Wright, and this is from 70s, and this is in a case that we have no noise. And let's see, what does it say? So it says this is NP. Recall, NP was in a sense the strength of our signal, right? So it was the average degree, right, that we had. So this NP is if larger than log n, then we can actually show that you can actually you can do alignment with probability going to 1. And this corresponds to this line that y equals -1. And if we look at this, so remember that this was basically to the left of -2 is where we don't have noise. So this is the noise-free region we are discussing. Now his result is saying that if you're basically below this -1 line, then so on one side, on the green side, you are you basically can learn the exact alignment. On the other side, you cannot learn it, right? So this is basically what his result is saying, right? This is exactly the line we get from this condition. So when is it possible to do this? And you have matching sufficient and necessary condition, right? So the converse meets the achievability. Then, not surprising, in this classical setting, we also have studied what's going on in terms of the algorithms, right? And these are results that show that we have indeed polynomial time algorithms in this noiseless setting. And some of these surprisingly are not even very old, right? It's from 2008, one of these algorithms that actually shows the existence of a polynomial time algorithm alignment. So when I put a blue in a region, it means that it is polynomial time algorithm, right? So the green was it's information theoretically feasible, red is not feasible, and the blue shows the computational complexity that you have a polynomial efficient algorithms there. So for the case that is much more interesting is actually when you have noise, right? And there is a result from 2011 from Pedro Pedrosani and Matthias Grossglauser, and they actually find the sufficient condition for this setting. And if we work out the math here, you end up getting this line 2y minus x is minus 1, which is basically all this green region that I'm showing here. So they showed that all of this is feasible to do, but this is an information theoretic result, and it's only sufficient condition, and we did not know what is actually the converse. So what my student Daniel showed in 2016 is that he tightened this bound, and if you see there is an 8 here, he tightened it to 2, and then he had also a necessary condition which they're not matching, right? Because the leading coefficient here is 1, the other one is 2. And then later on, he actually could prove that the sufficient condition is matching. So indeed, the necessary condition is tight, right? So this is what we needed to have. And what does this mean? It means in terms of this graph, now we get the red part on the bottom that tells you this is not feasible. And actually, for the entire positive correlation, we know when something is doable and when it's not doable information theoretically. So unfortunately, the situation with the algorithms is much more dire and not surprising, that's why I was trying to explain to you that this is a quadratic assignment. So, so you do not expect like nice algorithms necessarily everywhere. And what people have focused is mostly in a certain regime that they're looking at the sparse graph. So as I told you, this P is capturing the sparsity, and then recall that this S was your correlation in a sense that was capturing. You don't want this S to vanish too quickly, right? So there's a lot of algorithmic work in this area. And interestingly enough, all of these end up corresponding to the same line on this graph. So it's just the way I'm depicting the results in terms of these exponents. So all the interesting things are happening on this one orange line, right? But there's been lots of nice results here. And if you look at what's happening here is people are trying to get a handle on this S, right? How quickly this S is actually going to reduce, right? They're going to zero, the correlation, right? So this is what these results have been showing. And what is nice is that on that line, that orange line, you have variety of these polynomial time algorithms. So again, everything here is for this orange line here to this, to the left hand of the orange line, you get this results. Unfortunately, the green side is not as well studied. And interestingly enough, all of these polynomial time algorithms I mentioned are in this regime where S is bounded away from 0. So Boaz Barak and his students have a very nice result for the setting that actually allows your S to approach 0. But what ends up happening, so it's a larger setting they're studying, but what is not so good is that, you don't get a polynomial time, but you have quasi-polynomial time algorithms in this setting, right? So, and this basically, unfortunately, still, is in the same regime. So therefore, it does not guarantee any region to the right of this line. So let me show you this. So this green part is still, nothing is gone blue. So everything I told you so far has been in the setting that you have exact alignment. Hence, we had no mismatch vertices. We're interested in this almost exact. So you have vanishing fraction of misaligned vertices, or you can have a constant fraction, which is called so-called partial matchings. And there's some very nice results in this arena as well that are happening. And, folks have had some results in this. Especially, I really like the last one, which is Laurent Massoulier's work, which is fairly recent. Actually, it's this year. So, and then, we have these various sufficient conditions that people have derived for these pairings. There's also been some new results that people are looking at when you have dense graphs. And then in case of dense graph, indeed, this is Zhao Shu Yi Hong's work. And what they can show is that the result that we had with Colina, they can actually I apologize for my cat coming around if you hear the meowing. So this basically what they can show is that, you know, they can actually even improve on these results, even, you know, in this regime for the case when, you know, you allow for actually dense graphs, right? And then they get this matching bounds. Because if you recall, and I had to go a little bit quickly through this when we were discussing the results there, I was highlighting that there's some conditions, right? So it was looking at the sparse regime. So thank you so much for your attention, and I hope that, you know, this motivates some of the young folks here, which I'm sure are much smarter than me, to take a look at the what's happening in the region to the right of that orange line. And the second very interesting topic that I like to always, like, I think in the plenary one should also give some idea for people that perhaps they would do better than what we did, is that, as I mentioned to you, this graph matching problem is a quadratic assignment. And we know in some cases, quadratic assignment is actually not NP hard. There are special settings when, you know, this is easier. So it's very interesting for me to like understand exactly when we have these polynomial time algorithms in this problem, what kind of like properties does the matrix have, and why is this assignment problem actually easy in this setting? So I want to thank you for listening to me, and perhaps I'll have some questions. I don't know.
Well, let's thank Negar first. Thank you for a wonderful talk. Hopefully we can. Oh, thank you first, and of course, if anybody has any questions, please feel free to turn on your video and your voice. Anybody?
I
So
think it's
I have a question. So as the graphs get denser,
yes.
are you actually gaining information or losing? Because all the information embedded in they become more similar, right? Or
Yeah,
is
so
the
it's not
definition wrong?
clear, right? So what really, it's a very good question. So when your graph is, you know, so what matters is more what is happening in the intersection graph, right? Not just the density. Because of course you can imagine if they're completely dense and they're fully connected, there is no way, you know, but it depends on the automorphism graph of your intersection, right? So you can imagine that if they are complete graph, there's no way you can de-anonymize. So what really matters is, I think it's a great question, right? So we all assume that the difficult regime to look at is the sparse regime. And of course, you know, this is what most people worked on, but in by no means, if you have a dense regime, it makes the problem any easier. You still have to consider what's going on in terms of your strengths of your signal, right? So that's basically what the relevant thing is, that how is the intersection graph?
Right. And is there like a good cutoff between where the problems or the nature of the problems happen in terms of how dense or we're talking about?
So this is an excellent question, right? So basically let me just 1 second see if I can go back on my slides to show this to you, because I think I went too fast over that, right? And this is when I was giving the information theoretic results. So as you see, they're basically all these objects here that are making assumptions about both your noise and also, in a sense, denseness of your graphs. So I don't have a very clear setting to tell you like this is exactly where things get easier or harder, but all of these have some assumptions about like denseness of your graphs, right? As well as strengths of your signal. So what is here on the bottom line, this is in a sense the noise, and the one on the top is exactly what you're saying, right? So this is considering how dense is the graph.
Right.
But it's not that, you know, we know exactly how this changes as you vary the P. So in a
So
sense,
there's
what we have
something
looked at,
dramatic happening, right? Like as you
it
go.
might be a phase change, but it hasn't been studied as far as I know, right? So all the phase changes I have shown in my diagrams is that you assume that this is the sparse regime, and then I'm checking what happens to noise.
Right.
right? So what you were saying would be a very interesting graph as well, right? So you might either want to fix something here as well, like, you know, and then look at how things change with density. But it's something that, you know, we haven't looked at. But by no means, you know, it's not true that, you know, and I think it's a bit misleading that I think I even said it that, you know, it's interesting regime is the sparse regime, but it's actually misleading. It's not true. The dense regime is also very interesting. It can get very difficult there too. So your question is
Although in
right
practice,
on the money.
it's a little hard, right, to sometimes tell them apart between the dense but not
Absolutely.
really, and you know, the sparse with
So, you know,
with
there are two
degree.
sides. Like, let me give you the extreme, and then I think you would then appreciate that why both are difficult. And I think you already saw that. I am just saying it for maybe perhaps the students in the so on one side we care about sparsity, because if your graph becomes disconnected,
Right.
then there's no way you can tell it, right? You don't have edges. How are you going to find it? And this is exactly where that log n comes from, right? Because in the Erdős-Rajnyi, that is where your graph becomes disconnected. You have these isolated vertices, and when you have isolated vertices, you can't have perfect alignment. So it's a very obvious, in a sense, converse, right? The other extreme, and it becomes difficult again, is that if it's fully connected, then again there is no information, right? So absolutely.
Thank you.
Thank you so much. Excellent question.
Anybody has another question for Negar? No?
By the way,
In
you
that
know,
case,
I was excited that you're moderating this talk, because I remember when I came to your talk in 2016, or when it was, you know, you were looking at, you know, what kind of degrees in the directed graphs are actually degree profiles are graphable, right? This was the work you were discussing. And some of the algorithms here, specifically, I think one of the algorithms of Jiaming and Yi Hong that I was, I don't know where was the polynomial time algorithm. Sorry, it was. Yeah, so one of them is exactly using the degree profiles. So I think it's interesting, right, that in the sense that this is a signature that also could be used to do this anonymization.
yeah. In my case, usually the graphs are disconnected.
Yeah, I remember your talk. It was very interesting.
Cool. Well, thank you so much. It's been a pleasure, and I'm glad I got to moderate your talk. Well, so much again, and we'll see each other in person at some point, hopefully.
I hope so. Thank you everyone for attending, and I see a lot of familiar names here, so I hope everyone would have a good day or evening depending on where you are. Have a great one. Take care.
Thank you, Negar, also from my side.
Thank you, Danilo. Take care. Bye-bye.
Bye-bye.